Okay, good, right. Oh, except now you can't see. Can you see that?
I can just see it.
Try again. So can you see the right screen now?
I can see the screen, yeah.
Okay, there. Is that right?
Yep.
Okay.
Can everyone else see it? It's very funny on my screen.
Well, it's all red, but we can see it. I mean, we can, yeah.
Right, okay. So if you can, well, you can certainly read the two equations. On the left-hand side is the Gibbs equation. And it's very simple. It's the surface tension is sigma. And what that says is that the change in the surface energy on the left is equal to the free energy change of the bulk, which is the RT d log C, times how much material you transfer to the surface. It's a really simple equation of two free energies. But the world divides into the equivalent of vaxxers and anti-vaxxers, into Gibbsers and anti-Gibbsers. And there are a certain number of anti-Gibbsers around who believe that because this equation fails on many occasions, there's something wrong with it. There's nothing wrong with it. At the bottom, if you can see, I've written the snag about the Gibbs equation is it's like all great thermodynamic equations. Sigma is easy to measure. Gamma is the thing you'd really like to find out about. So all you have to do is measure sigma as a function of concentration or activity, and you get gamma. The problem is that the Gibbs equation applies to everything in your mixture, which includes rubbish at sort of parts per million. This is because the Butler equation, which is on the right, which isn't so much talked about, says equilibrium is reached when the partial surface tension of every component is equal and equal to the total. And that means that if you've got a tiny trace of something that's very surface active, it will simply push everything else off the surface. So that's the problem with Gibbs. It needs to be really useful to have a technique that measures directly what's at the surface. And that's what neutron reflection does. Okay, next slide, just click. Oh, that's better. So this gives rise to a number of anomalies, the problem with the Gibbs equation. And what I've selected here are 4 anomalies. There's trace ionic impurities. Of course, there are trace ionic impurities, depletion, and so on. So Tom, if you could press particularly on the left hand in the middle, go in the middle and click in the middle, right? Okay. So here's an example of an ionic impurity, sorry, a non-ionic impurity. The system is, I'm sorry, you don't have my pointer to guide you, but it is dodecanyl carnitine, which is an amino acid with a long chain on it. So it's a typical surfactant. I shan't give any formulae of surfactants. They're just long chains and head groups. In the bottom, in C, you will see that, well, sorry, this hydrolyzes to give you dodecanoic acid, which is very surface active at extremely low concentrations. The bottom slide shows the solubilities of dodecanoic acid. And if we look at pH 2, you'll see the solubility is really, really low. And if you compare it with the top A, where the CMC is, they're all on the same concentration range. You'll see that the solubility limit of dodecanoic acid is very, very much lower than the CMC of the surfactant. So what happens when you measure the surface tension, as you increase the concentration, you reach a point where there's sufficient dodecanoic acid, that it occupies the surface. So what you have in A is the surface tension at pH 2 goes through a sharp dip. But then, of course, the surfactant micellizes and it solubilizes it and takes it back into solution. So that's the classic dip. Now, unlike the normal examples where no one knows what the hell's going on, here you can play around with the situation. So if you push the pH up to 7, that's the black in C, then the solubility changes by more than an order of magnitude. It's much higher. It's now much closer to the CMC of the surfactant, and it never rises to a concentration where it can cause any surface interference. So the black curve in A is the normal surface tension curve. The green one, you can also up the solubility by adding electrolyte. And that, while it doesn't do it very much, you'll see by comparing that with the surface tension that it's enough to stop any anomalies. The middle one shows the actually what happens to the surface excess when you measure it with neutrons, in a case where you're not distinguishing between the two components. And there you can see the huge maximum at pH 2. Okay, if you click, and now when you click on the right-hand corner, no, top corner, that's it. So this is another problem that crops up with surface tension measurements. If you, many surface active things are surface active at very low concentrations. You can look at the concentration scale at the bottom. So if you look in the region of 10 to the minus 6 molar, you run into a problem which is that the amount of material that absorbs at the surface depletes the solution. So what happens is the solution concentration decreases much faster than it should as you lower the apparent concentration. And when that happens, of course, you must shoot off towards the surface tension of water. And you'll see in each of these, there's a region marked A and a region marked B, and there is a change in gradient between these regions. And in each of these 3 cases, this has been interpreted as micellization. But it's not micellization. It is simply that when you reach that point, you start to remove material from the surface. Now, if you measure it with neutrons, the first thing you can see is the neutrons and then the reconstituted Gibbs equation are the red lines, and they go through all the points below the break, but they don't go through the points at the break, and they do extend in measurement beyond where the break occurs. So what that tells you is this is just an anomaly. The depletion it's a real effect, but it's not related to the true system if you had enough material there. So the top one is a pluronic, and that's for a long, I think people still believe that that AB intersection is a CMC. The polyvinyl ether doesn't have a CMC, and that break we measured ourselves, that is simply depletion. The middle one, we've done separate neutron measurements, but that is actually from the original publication. I shan't name any names, and that was identified as a CMC, but it certainly is not. And one way of telling is that the surface coverage in region A is ridiculously high. Okay, if you click and go to the left-hand bottom corner. And now another problem is that when you looked at the Gibbs equation, it's got a concentration, a bulk concentration or a bulk activity term. You don't always know that. And there are 2 occasions when it becomes a problem. The first is when you get ionization. If you look at the Gibbs equation on this slide, I've now rewritten it. It's not very clear, but you've got your d sigma on the left, and then on the extreme right, you've got RT log gamma mxz or something, and then there's a prefactor p. So if you've got an ionic surfactant, the prefactor is 2, because you're losing the free energy of the surfactant ion and the counter ion. But in these surfactants shown in this transparency, these are Gemini surfactants. And you can see from the diagram on the right that each one has 2 head groups, nitrogen plus, and 2 chains, and they're separated by a spacer. And that shows the 2 packed in a way that would be very convenient and rather likely. And it would also obviously not be surface active because you've got charge at both ends. Now, an isolated one of those molecules will have a Gibbs prefactor of 3. Now, you don't know what the prefactor is when you measure the surface tension, so you assume it's 3 and you get an area. But then we come along with neutrons and we don't have to worry about any models, we just measure it, and then we compare our area with the surface tension value. And we say, well, actually, and if you look at the graph, if you've got a large spacer, you are quite close to 3. Indeed, the measurements give you 3 and the curve doesn't. But when you go to shorter spacers, the Gibbs prefactor goes down almost to 1. Now, what that means is that in the solutions of the small spacer ones, you are getting aggregation in the bulk solution. Doesn't say anything about what's happening at the surface. You're getting aggregation in the bulk solution, which is probably a mix of dimerization as shown and ion neutralization. But you haven't a clue that that's happening from the surface tension measurements. So again, you get the neutron measurements, combine them with the Gibbs equation, and the whole thing becomes a very powerful method of analyzing. Oh, if you could go back now, Tom. And go to the bottom right, yes. Now you can have the opposite. And this is a very interesting case because we didn't expect it. This is a hydrophobically modified polyacrylamide, okay? And it's got about 1 in 50, well, it's got either 1 in 50, 1 in 100, or 1 in 200 basic residues attached to a C12 chain. And the diagram on the left shows the schematic structure of it. You get a lot of hydrophobes form the surface layer. You've then got quite an interesting problem in the analysis in that you've got to have all the surfactant attached. And although that's a low scattering length, it contributes significantly. And you are going to get the occasional hydrophobic group tangled up in the mess. But on the right-hand top, A, that is, you get a measurement of the segment excess, that is, not hydrophobic groups, but the number of segments. And it goes exactly as you'd expect. The more surface active one is the 1 in 50, and the least surface active one is the 1 in 200. Now, the surprise in this is that when you measure the surface tension, at first you say, that's B there, that all looks sensible. The the 1 in 51 is more surface active than the 1 in 200. But the problem with the diagram, which is not obvious, is that the surface coverage is so low that the slope should be nearly 0. So these are all much more active than they should be. This is the opposite of the deuterionics. Then turns out, we found out that polyacrylamides often hydrolyze to a very, very small extent. And when they hydrolyze, they acquire a charged group. Indeed, it's used commercially to boost the solubility of acrylamides. So if you say, well, suppose we've got 1 charged group for every hydrophobe, then you get the 3 solid curves when you fit the surface tension using the actual measured surface excesses. if you assume that the charge is uniform, irrespective of the hydrophobic groups, you get the dotted lines. And clearly this indicates these results, taking the neutrons and the surface tension together, that you have you've got charge groups. And that means that you can't interpret the surface tension on its own. Okay, back you go. Right, we'll now move on. The other impurity that crops up a lot, and this plays absolute havoc with the surface tension measurements, is you get charged groups. And in this slide, I'm looking at adding aluminium ions at a very low concentrations, the concentrations given in A up at the top, to a solution of an anionic surfactant whose surface tension is shown as the black rings in B, and that's the normal surface tension. Now, if you add tiny traces of aluminium in that middle one, you'll see the surface tension shoots down, and you've got the surface tension decreasing at very low concentrations, and then reaching a region which is at the very bottom is a little bit flat. And in fact, there's marked just the top of where there's proper phase separation, and there's a precipitate. But what's really interesting is what the neutrons see, and that's up at the top. So they're scaled, those, by the way, so don't try and compare the absolute reflectivities. But the red and the black are the surfactant on its own and with very little aluminium, and they show the normal monolayer. But when you up the aluminium, you see a fringe first, and then you see two fringes. And when you analyze that, that corresponds in the one case to a monolayer plus a bilayer at a little gap beneath the surface. And in the green case, where you've got two fringes, corresponds to two bilayers underneath the monolayer. It's a very interesting structure and very widespread. We've seen it in a lot of systems now. The phase diagram is interesting too. So that's at the bottom. The grey shady line running down near the bottom is the separation of the bulk one-phase region from the bulk two-phase region. And the coloured shaded bits correspond to the S0 is the monolayer, the blue S1 is the monolayer plus fringe, and the yellow is the monolayer plus two fringes, and there's even a region where you get multi-layers. But what you'll see is that the surface layers occur, if you look at concentrations of the surfactant of about 4 to 6 millimolar, below the concentration at which bulk phase separation occurs. Now that's an area where the surface tension just wouldn't be able to cope at all. Okay, on to another one, example. Right, so I've used the surface tension to, the Gibbs to explain and the neutrons to explain anomalies. But one of the great things about combining them is you start to understand situations that you wouldn't otherwise understand. And I'm just going to give you a brief look at what happens when you mix a polyelectrolyte with a surfactant. Now, this has caused endless puzzles and controversies and arguments about equilibrium. I'm just going to give you a simple story here. We'll look at the right-hand part there first. On the bottom is the measured binding curves as measured by other people. The black is a plot of the amount of surfactant attached to the polymer against the free surfactant. The red is the transferring that into total surfactant. The problem is the surface tension is measured as a function of total surfactant. So if we look at the surface tension, region A, in that region, the surfactant is binding to the polyelectrolyte. And to do with that prefactor I talked about, the slope of that curve is approximately the same as you'd get from surfactant on its own, although not at such low concentrations. So that is simple surfactant binding to the polymer. Now, the activity of the surfactant is the free surfactant in the concentration. It's not the total surfactant. And the free surfactant in the binding curve goes through a range where it hardly changes at all. It's almost vertical. That's the Satake-Yang binding isotherm there. And if the free surfactant doesn't change, then the activity doesn't change and the surface tension doesn't change. That is the plateau B here. So all this time neutrons are measuring, we've got surfactant there, we can measure it, but the surface tension is sloped here and flat here. And the composition of the layer is absolutely the same all the time. Once you've completed binding surfactant on the bulk polymer, then the free surfactant concentration, the top of the binding curve, starts to increase fast again, very fast, faster in fact than the bulk concentration. And so the surface tension in region C plummets down, and actually the whole thing precipitates somewhere in that region. Now, what's really interesting is when you swap over to no electrolyte. First of all, the binding shifts to a much, much lower concentration, though it's otherwise similar. And then we have this very peculiar result. There is no surface tension drop in the first chunk while surfactant is binding. And this is because there's no electrolyte. And what's happening here is a Manning condensation. In the Manning condensation, the activity coefficient effectively means that the activity remains very low and constant until you get out of that. But it doesn't mean there's no adsorption. So you measure quite strong adsorption even up at that high value in region A. As you bind surfactant to the polymer in the bulk, you might expect it to become more surface active, but it doesn't, because the free surfactant stays very similar, i.e. there's no change. So again, you get a plateau B, which prolongs this. When you've completed cooperative binding and you're on the more gradual slope there, then the free surfactant increases extremely fast, faster than the total surfactant. And so in the Gibbs plot, you get a very steep gradient. And the dotted line there, red in C, is calculated from the measured coverage from neutrons and the binding curve, which gives you the activity. So you perfectly reproduce that plummeting drop, and then it precipitates there. If you reduce the polymer in the green, then of course you complete binding at a lower concentration. So region C starts at a lower concentration, and it all becomes relatively straightforward. There's much more to explain, and I would have to say that's taken us 20 years. So next one then. Right, over to mixing. So this is now to do with Butler's equation. And I'm not going to go into the equations for this. They're a bit complicated. I've got them if anyone wants to see them. We're just going to go starting with ideal mixing. So the great thing about neutrons is mixtures are really easy to measure the composition of at surfaces. You just deuterate one, and then you deuterate the other, and you just measure it. It's really easy. And what's more, you can do it above the CMC. With surface tension, it is possible in principle to measure the composition, but you have to use the Gibbs equation with keeping one constant and then doing it for the other way, and it takes a lifetime. So although the theory I'm using here was developed before neutrons, the applications were very poor, and no one understands surface mixing as a result. But it's very, very important. All applications use mixtures. So let's start with ideal mixing. The top system contains two surfactants and they only differ in their chain length. And obviously the longer chain length is more surface active. And the actual composition we use here is a eutectic mixture of 2 C16 to 1 C18. And the first thing you notice when we measure the composition at low concentrations is the C18, although at lower concentration, absorbs much more strongly. The surface is 80% C18, although the bulk is only 1/3. And that destroys the first myth. When I first went up to Unilever, people swore that the surface composition was the same as the bulk solution. Well, it isn't, and that's ideal. When you reach the middle there, you hit the CMC, and at that point, things start to cluster, obviously, in the micelles, and the C18 will micelize more readily than the more strongly. And so you now get a new fractionation, and the composition at the surface drops because of the micelle composition and the mixing at the surface. Eventually, at very high concentrations, since all the material is in micelles, the majority of it is, this must come to the nominal 2:1 concentration. And obviously, that's about where we're heading. Right. In the one below, these are also fairly ideal, but they're different size. One's got a very large head group, and one's got a very small head group. The large head group will be expected to be less surface active and to micelize more readily. So if we look at the behavior, again, we've got rather, I won't go into the details at very low concentrations, but again, it's the red one, which is the C12E3, which is the more surface active, that goes to the surface. At micellization, there's a break and they'll start changing down again. But now, interestingly, instead of reaching the bulk, this persists. This lack of symmetry for the 50-50 remains, the 50-50 of the circles, even at high concentrations. So here's a situation which is different again. Okay, next one. Now, those were ideal, but what we have to do is allow for interactions, and here things get a bit complicated. So the normal assumption for bulk solutions is to take that expression for the free energy at the top and say that the B value is a parameter which is constant, and then, for example, at 50, when x1, the mole fractions of x2 are both half, then that's where the minimum in the free energy occurs. So mixing is optimized by the free energy of mixing if it's negative. And the example shown here is SDS with C12E3 in the black, and you can see that is pretty symmetrical. But actually, while that may be quite reasonable for bulk solutions, it's not reasonable for surfaces, because in a flat surface, the packing will tend to be hexagonal, and 1:1 is not optimum. So what we find more often than not is the surface mixtures are have what we call a cubic term in the free energy shown at the bottom there. That's not an arbitrary expansion. That is an expansion which was done many years ago by Redlich and Kister, which takes into account that the Gibbs-Duhem equation, which relates the activities of the two components, is strictly related. They're tied in, and that free energy satisfies that condition. And we found that it works extremely well in describing these systems. And you can see here two examples where we've changed the head group of the non-ionic surfactant and shifted the minimum right over to the right there. And similarly for the E12, although the E12 is now getting very weak. So now we're starting to look at the lack of symmetry in the mixing. Next one. Okay, now this is a more adventurous one. These are a pair of surfactants from a bacteria which is usually thrown or unloaded in tons onto oil slicks. This bacteria has this pair of surfactants are extremely surfactive, and what they allow the bacteria to do is to solubilize the oil and basically eat it. So they interact very strongly. And so it's interesting to explore this. And not only that, but because of their reputation for getting rid of oil slicks, they've become rather favored in eco-detergent systems. So they're now in common use. So the only difference between these is one has one sugar head group and one has two sugar head groups. We don't need to bother about that. But we've analyzed the surface tension, and what should be clear from what I've mentioned is that measuring this surface tension and composition with neutrons actually tells you about what's going on in the micelles as well as the surface, because the micelles also control the surface. And here, the micellar mixing is almost ideal, and that's shown as the blue line, which shows one of the monomers, shows its composition as a function of total mole fraction, and it doesn't deviate much from the diagonal there. If we were to calculate the ideal mixing at the surface for that, we would get the red line. As it is, the experimental line shows that we've got quite a strong and unsymmetrical interaction here, and that's fitted to the experimental points there. The surface values of B and C, when their magnitudes are the same, that means that the minimum is at 1/3 composition, or 2/3, depending on the cell. So let's move on from that. Now, you should realize that most detergents consist of a lot of surfactants. And this is the combination of 3 that is often the base of most detergents. And this raises the question, how do you handle the calculations? Well, the calculations are quite easy to handle, actually. They're very long to write down, but they're quite easy to handle. You take the pairwise interactions, so we measure all the pairs here, and then we just calculate them for the mixture as a function of composition. There's no added information. And my memory of triangular phase diagrams, which is shown down on the left, was my first undergraduate physical chemistry experiment at university. And I'm astonished I continued, to be frank. They're really difficult. And we've attempted here to show it in color. And I won't go into it in detail, but if you can see the white asterisks, that means the fit is quite good, because there's a background dot that otherwise obscures them. Like in the top left-hand one, there's a blue dot and a red dot, where clearly the fit is not very good. But I'm putting it up to say, with neutrons, we can just interpret all of this really easily. You now can't use surface tension. That's too difficult for these. Okay, next one. But if you're a serious surfactant person, then your fairy liquid contains at least 10 surfactants, and it is an extremely effective product. So we thought we should advance, and we actually took those pseudomonas surfactants, mixed them with that basic one, which I've just shown you. And here, there's no way of plotting this, but we've plotted the binary pairs, and you can see it all fits. That's just taking all the binary interactions with quadratic, cubic, and quartic terms and calculating. And of course, all these are measurements using neutrons. It took a lot of work, but we can now really attempt to understand these mixtures. One easy observation is, when you've got a pair like R1 and R2 that interact very strongly with each other attractively, that combination will push off the others. So once you start realizing that, you start to see why it's so advantageous to mix some of these things. And then during the wash or whatever, the concentration changes, and then the mixing pattern will also change. That is the surface mixing. Okay, next one. Okay, this is really a final slide. One of the other things you like to do with detergents is you use them to spread additives onto surfaces. In this particular case, these are perfumes that you use to make the wash smell of, well, if you use linalool, they smell of lemons and so on. But there are lots of other applications with coating different surfaces other than for cosmetic regions. And the question is, can you use these models, which will have the same lack of symmetry and so on, to account for the perfume behavior? So here we've done it for two systems. And what we've done is we've tried to use simply the solubility limit of the linalool and the phenyl ethanol instead of the CMC. And lo and behold, it works absolutely perfectly. So if you look at B, you'll see that a very flat presence of PE and linalool occurs at the surface. It varies very little over the whole range, but the calculation accounts for it beautifully. And this again really occurs because there's a minimum in the free energy of the two perfumes with the surfactant at a very low concentration, not at the normal 50-50 where you'd expect it. And it's this that sustains this long absorption here. So this is another example where actually, again, surface tension would give you almost no information, and neutrons are supreme. Okay, and that brings us to the next one, which is my acknowledgements. Okay, I haven't put any references in that because it's part of, or the large part of, a review written by Jeff Penfold and myself, which will appear in PCCP. And so I'm very indebted to him for this help. And then there are actually many people there with a lot of industrial help, which has been brilliant at not so much helping us, but finding good problems for us to solve, and an awful lot of other people. And thank you. I hope that was all right.